Welcome everyone, my name is Chu. Today I'm going to show you how to address matrix eigenproblems. At the outset, why are we going to learn this? This is essential since it plays a pivotal role in the diagonalization of matrices, which is useful in mechanics, quantum physics, and other future critical issues. Thus, if we are adept at addressing eigenproblems, then it will be remarkable to our future process of learning. Okay, so let's move on. First of all, what are eigenproblems? Considering this kind of matrix equation, AV equals lambda V, where A is a matrix, V is a vector, and lambda is a scalar quantity. We name this kind of equation eigenvalue equation. Okay, so if we want to infer the vector and the scalar quantity from this type of equation, then we will call this sort of question eigenproblems. Next, I would like to introduce a novel perspective to you. That is inertial tensor in mechanics. Okay, let me ask you a question first. What is the eigenvalues and the eigenvectors of this inertial tensor for the homogeneous cube? It equals m times b squared times a 3 by 3 matrix whose diagonal elements are 2/3 and other elements are all negative 1/4. You may notice you're not familiar with the approach to obtain the eigenvectors and eigenvalues, right? So, how do we solve this question? To solve the problem, let me first present some preliminary knowledge to you. Okay. Number one, there's a theorem stating after the diagonalization of any matrix completed, the diagonal elements of the matrix can be its eigenvalues. Second, there's another theorem claiming eigenvectors of a Hermitian matrix corresponding to different eigenvectors are orthogonal, where the definition of a Hermitian matrix H is defined as H equals its conjugate transpose. And the proofs of these theorems are embodied in mathematics physics textbooks. Well, we only emphasize the applied aspect here. So, provided you are interested in these inferences, then you can check them out by yourself. Okay. Number two, the concept of linear independent and dependent. Consider the matrix equation K 1 times A1 plus K2 times A2 plus K3 times A3 equals 0. A1, A2, and A3 are non-vectors, and let capital C be the component matrix and vector K be the coefficient vector. That is, capital C has 3 rows that consist of the x, y, and z components of each vector A, and vector K is defined as a column vector which consists of K1, K2, and K3. Then the equation can be represented by capital C times vector K equal 0. Now our task is to solve the solution, right? Namely, the loaded combinations of K1, K2, and K3. Notice that the meaning of this equation is to observe the relation between A1, A2, and A3, whether they are collinear, coplanar, or are they just too peculiar to exist for this equation. In fact, there are three distinct results in this situation. No solution, only one unique solution, and innumerable solutions. However, it is evident that the combination of 0, 0, 0 is always allowed to exist in the equation. Therefore, we only have these two results, only one unique solution, and infinite solutions actually. On the other hand, the geometry concept of the determinant of three vectors is that the absolute value of the determinant consisting of the three vectors is the value of the parallelepiped. In addition, if the determinant of capital C equals 0 if and only if after the row reduction of capital C finished, we would obtain at least one row of 0, 0, 0 in capital C. According to the geometric concept, the value of the parallelepiped consisting of the three A vectors equals zeros means A1, A2, and A3 are coplanar, or two of them are collinear. Since the determinant of capital C equals 0 is equivalent to the value of the parallelepiped equals 0, we obtain the equation has infinity solutions. For example, A1 and A2 are collinear, then A1 equals any real value times A2. Therefore, we would conclude A1, A2, and A3 are linear dependent if and only if the determinant of capital C equals 0. By the way, the meaning of dependent is to point out they are relevant. Okay. On the other hand, if the determinant of capital C doesn't equal 0, if and only if after the row reduction of capital C finished, we would realize none of the rows are 0, 0, 0 in capital C. According to the geometry concept, the value of the parallelepiped consisting of the three A vectors is larger than 0 means A1, A2, and A3 are not coplanar. Additionally, two of them are also non-collinear. The value in this case has a certain value, and since the determinant of capital C doesn't equal 0, equivalent to the value of the parallelepiped doesn't equal 0, we obtain the equation has only one unique solution, that is, the combination of 0, 0, 0. We would conclude A1, A2, and A3 are linear independent if and only if the determinant of capital C not equal 0. By the way, the meaning of independent is to point out they are irrelevant. Okay, now I can start to demonstrate the step-by-step guide for addressing eigenproblems. For convenience, we are just consider two-dimensional eigenproblems now. First, let me reposition the term of lambda times v to the left-hand side of your eigenequation, just like this. Okay. Notice this symbol represents an unit matrix. Okay. Since we tend to solve eigenvectors and eigenvalues from this equation, and we are not interested in the trivial solution, that is the combination of 0, 0, right? We engage in the case of infinite solutions to obtain other solutions rather than the trivial solution. Thus, we let the determinant of A minus lambda times a unit matrix equal 0. Okay. After the calculation, it's just a question related to solving a polynomial equation, right? So we can obtain the values of the lambda now. By the way, we usually call this equation characteristic equation. After the acquirement of every lambda's value, we can proceed to put these values of lambda into the matrix equation parentheses A minus lambda times a unit matrix parentheses times V equal 0 to obtain each normalized eigenvectors. Okay. For instance, there's a matrix A which has a first row of -2 and the square root of 5 and a second row of the square root of 5 and -6. Then, how do we find its eigenvalues and eigenvector? First of all, we can rearrange the equation to be like this. Since we are only interested in the case of infinite solutions, let the determinant of A minus lambda times a unit matrix equal 0. After the calculation, we can obtain the values of the lambda are -1 or -7. Since the lambda is the eigenvalues of A solved for, right? We finished the process of finding its eigenvalues. Okay. Let's proceed to find its eigenvectors. When lambda equals -1, we can put the value of lambda into our eigenvalue equation. Okay. Then we will obtain the first normalized eigenvector is a column vector, the square root of 1/6 times the square root of 5 and 1. We can use the same strategy to obtain another eigenvector. Now we can finally return to solving our initial problem. First, I will assume the symbol of the inertial tensor's eigenvectors is omega. Next, write down the eigenvalue equation like this, and let the determinant of the inertial tensor minus lambda times a unit matrix equal 0. However, you may notice the determinant below is quite tough to calculate, right? And due to this reason, we can simply find the determinant through row reductions first. Here, let the second row minus the first row, and we can obtain this equation. In addition, we can proceed to simplify it by extracting 11/12 m times b squared minus lambda from the second row, right? Subsequently, let the third row minus the first row and extract 11/12 minus lambda again. Now, the determinant is dramatically easier to solve than the original one, right? And the result is displayed in the last equation here. Since we have simplified it to become a polynomial equation, we can effortlessly solve the value of lambda by these steps. Then here are the results. We successfully obtained the eigenvalues. Moreover, based on our first theorem, the diagonalized inertia tensor is also solved, right? So now it's time to solve the eigenvectors. When lambda equals 1/6 m times b squared, the eigenvalue equation looks like this. Okay, since we only need two equations to check the relation between three elements in the eigenvector, therefore we can focus on the first row and the second row of the product of the inertia tensor and the eigenvector. Here are the first relation and the second relation. After the calculation, we can obtain x equals y in the eigenvector. Then we apply this relation into one of the three products of the inertia tensor and the eigenvector. We can obtain x also equals z in the eigenvector. Therefore, the first eigenvector is the square root of 1/3 times the counting vector of 1, 1, 1. Next one, when lambda equals 11, 12 times n times b squared, it is noticeable that each relation of the product between the tensor and the vector is identical. However, in this kind of case, we cannot obtain the relation between the three elements of the eigenvector. Admittedly, we have to find another approach to solve this problem. Since the inertial tensor is a Hermitian matrix, we can know the eigenvectors corresponding to different eigenvalues are orthogonal by our second theorem. Therefore, the remaining eigenvectors omega 2 and omega 3 will lie on the plane which is orthogonal with the omega 1. According to each identical relation of the product between the inertia tensor and the eigenvector, we can arbitrarily set the remaining two eigenvectors with the limitation for lying on the plane whose normal vector is parallel with omega 1. For instance, we can set omega 2 equal the square root of half times a column vector of 1, -1, and 0. Due to the orthogonality and the limitation, we can set omega 3 equal the square root of 1/6 times a column vector of 1, 1, and -2. Okay, we're done. To summarize, how do we address matrix eigenproblems? We will write down the eigenvalue equation, then follow the procedure to solve the matrix eigenvalues and eigenvectors, right? After you obtain the eigenvalues, we can directly write down the diagonalized form of the original matrix by filling diagonal elements with eigenvalues. Notice that the sequence of filling eigenvalues into the matrix is not unique. You can organize the sequence arbitrarily, with the understanding that you just change the sequence of the basis elements for this matrix. The basis elements sequence can be also determined by our decision. Okay, thank you for watching.